Hey everyone, and welcome to another deep dive. Today we're taking a look at something pretty vital to us all, the Earth's atmosphere.
It really is amazing when you think about it.
We walk around every day breathing, living, completely reliant on this layer of gas.
And most of us don't even think twice about it.
Right. So before we get into all the fascinating details, let's start with the basics. What exactly is the atmosphere?
Well, in the simplest terms, it's a mixture of gases.
Okay, held to the Earth by, what, gravity?
Exactly. Gravity is what keeps it all together, and it acts like a giant protective shield for our planet.
A shield, huh? What do you mean by that?
Well, it blocks a lot of the harmful radiation coming from the sun, and it also plays a huge role in regulating Earth's temperature.
So it's like a giant blanket keeping us warm enough to survive.
In a way, yes. It's all about maintaining that delicate balance that makes life possible.
Life as we know it, right? Because without the atmosphere, Earth would be
A barren, airless rock.
pretty inhospitable, to say the least.
Right.
Okay, so we've got this protective layer of gas surrounding the Earth. What's actually in it? What's the air we breathe made of?
You know, a lot of people think oxygen is the main ingredient,
Yeah, I can see why.
but it's actually nitrogen that takes the crown.
Nitrogen? Really?
It makes up a whopping 78% of the atmosphere. Oxygen comes in second at around 21%.
Wow, so all that nitrogen we're breathing,
Mm.
what's it doing for us?
Well, we breathe it in and out, but our bodies don't actually use it directly.
So it's just kind of passing through.
Essentially, yes, but that doesn't mean nitrogen isn't important for life on Earth.
Ah, I see where you're going with this.
It's essential for plants. They need nitrogen to grow, but they can't just grab it from the air like we do with oxygen.
That's right. Plants get their nutrients from the soil.
Exactly. So they rely on bacteria in the soil that can convert nitrogen into a form they can actually use.
A whole underground operation just to feed the plants. Okay, that makes sense for nitrogen. But oxygen, now that's got to be the stuff we actually need, right?
Sure.
Absolutely. Oxygen is the key to respiration, the process that provides energy to our cells.
And this is where we humans step in, breathing it all in.
Well, we're definitely part of the cycle, but guess who the real oxygen heroes are?
Let me guess. Plants.
You got it. They release oxygen as a byproduct of photosynthesis.
Amazing. So plants are crucial for both the nitrogen and oxygen cycles. I'm starting to realize just how interconnected everything is.
Yep.
But I know there are other gases in the atmosphere too.
Oh, absolutely. Carbon dioxide, for example.
Ah, yes, carbon dioxide, the one that gets a lot of attention these days.
It definitely has a bit of a mixed reputation.
Well, yeah, because it's essential for plants to grow, right? They use it during photosynthesis.
That's right. And then, of course, humans and animals breathe it out as a byproduct of respiration.
So it's all part of this natural balance we keep talking about.
Mm-hmm.
But then we have the whole climate change issue.
Right, and that's where things get a little complicated. The problem with carbon dioxide isn't that it exists, it's the increasing amounts we're adding to the atmosphere.
By burning fossil fuels, you mean?
Exactly. That's throwing off the natural balance and leading to all sorts of consequences.
Okay, so we'll definitely dig into the climate change side of things later. But I'm curious about the structure of the atmosphere itself. It's not just one big blob of air, right?
You're absolutely right. It's definitely not a homogeneous blob. Think of it more like a layer cake. Each layer has its own unique properties and functions.
A layer cake. No, that's an image I can get behind.
We've got 5 main layers, starting with the one closest to Earth, the troposphere.
That's where we hang out, right? Down here on the surface.
Yes. And all that dramatic weather we experience, that all happens in the troposphere. The rain, the wind, the clouds.
So all that drama is packed into a relatively thin layer.
It's where all the action is.
What makes it so dynamic?
Well, for starters, the troposphere is where most of Earth's atmospheric water vapor resides. And temperature also decreases as you go higher in this layer.
Okay, I can see how that would create some interesting effects. So what's above the troposphere?
Next up is the stratosphere, which is much more stable than the troposphere.
Stable in what sense?
The temperature actually increases with altitude in this layer. It's home to something pretty crucial, the ozone layer.
Ah, yes, the ozone layer. Isn't that what protects us from those harmful UV rays from the sun?
Exactly. Without the ozone layer, we'd be in big trouble.
So it's like our planet's sunscreen.
Pretty much. It absorbs most of the sun's harmful UV radiation, making life on Earth possible.
Okay, the stratosphere is sounding pretty important now. What happens as we go even higher?
Well, then we have the mesosphere and the thermosphere.
Those are...
They're way up there, extending pretty far out from Earth's surface. They play a key role in protecting us from meteors.
Wait, meteors? How do they do that?
As meteors enter the atmosphere, they encounter a lot more air resistance in the mesosphere and thermosphere.
Ah, so they burn up from the friction before reaching the ground.
Exactly. They create those bright streaks of light we sometimes see in the night sky, shooting stars.
Wow, those layers are like our cosmic defense system.
They also facilitate global communication.
Wait, how do they do that?
Well, within the thermosphere, there's a region called the ionosphere.
The ionosphere.
Yeah, that's where solar radiation ionizes atmospheric gases, creating a layer of charged particles. And this ionized layer reflects radio waves back to Earth.
So it's bouncing radio waves back to us.
Precisely, allowing us to send those signals around the world.
So that's how we can listen to radio stations from across the globe. Pretty incredible.
Yeah.
So we've got the troposphere, the stratosphere, the mesosphere, and the thermosphere. What about the last layer?
Ah, the exosphere. That's the outermost layer, where the Earth's atmosphere gradually fades into the vacuum of space.
It sounds pretty empty out there.
It is. The air is extremely thin in the exosphere, so thin that atoms and molecules can actually escape Earth's gravity.
So they just drift off into space?
Some of them do. Others might get swept away by the solar wind or captured by other celestial bodies.
It's mind-boggling to think about those tiny particles venturing out into the vastness of space.
It really is, and it highlights how interconnected everything is, even at that cosmic scale.
Okay, so we've covered a lot of ground here.
We've only just scratched the surface.
Before we move on to the world of weather and climate, I have a couple of questions about some of the things we've touched on. First, you mentioned the ozone layer protects us from harmful UV radiation. Can you tell me a bit more about what UV radiation is and exactly how the ozone layer acts as a shield?
Sure. So the sun emits a wide range of radiation, including ultraviolet radiation or UV radiation. And there are actually three types: UVA, UVB, and UVC. UVC is the most harmful, but luckily it's completely absorbed by the atmosphere before it reaches us.
Okay, so that's one less thing to worry about. What about the other two types?
Well, UVB is the one responsible for sunburns. It also plays a role in skin cancer.
So that's why we wear sunscreen.
Exactly. UVA can penetrate deeper into the skin and is linked to premature aging. Now, the ozone layer, mostly in the stratosphere, absorbs most of that harmful UVB radiation, and it absorbs all of the UVC.
So it's really doing a lot of heavy lifting to keep us safe.
It's crucial for life on Earth as we know it.
Okay, my second question.
Yeah.
You mentioned the ionosphere and how it helps with radio communication. I'm still a little fuzzy on how it actually bounces radio waves back to Earth. Can you elaborate a bit on that?
Absolutely. The ionosphere is full of ions and free electrons.
Ions.
Charged particles, basically. And these are created when solar radiation ionizes the atmospheric gases. Now, when radio waves, a type of electromagnetic radiation, encounter these charged particles in the ionosphere, they interact. And depending on the frequency of the radio waves and how dense the ionosphere is at that moment, they can be reflected or refracted.
So they bounce off the ionosphere and come back down to Earth.
Yes, that's one way to think about it. This reflection is what allows radio waves to travel beyond the horizon.
That makes sense. So it's all thanks to this charged layer in the atmosphere that we can listen to radio stations from across the world.
Pretty amazing, right?
Okay, I think I've got a good grasp on the composition and structure of the atmosphere now.
Great, because now we're ready to dive into the forces that shape our weather and climate. Welcome back. Now, are you ready to unpack the science behind our everyday weather?
Absolutely. I'm fascinated by how all these different elements come together to create everything from a sunny day to a raging thunderstorm. What's the driving force behind it all?
Well, it all starts with the sun, of course. The sun's energy is what drives our weather systems. Remember how we talked about insolation, that incoming solar energy?
Yeah, and how the equator gets more direct sunlight, making it warmer than the poles.
Exactly. And that difference in heating is what sets everything in motion. It creates temperature gradients, leading to air circulation patterns all over the planet. So that warm, moist air at the equator, it rises.
Because warm air rises.
Right. And when it rises, it creates an area of low pressure.
Okay, and as that warm air goes up, it starts to cool, right?
You got it.
Oh.
And as it cools, that water vapor in the air condenses. That's what forms clouds. And often, that leads to precipitation.
So that's why we see so much rain in tropical regions. It's like a giant natural convection oven, constantly churning out warm, moist air and creating those incredible downpours.
That's a great analogy. Now, as this warm air rises at the equator and starts moving towards the poles, it gradually cools down and becomes denser.
Okay, so denser air sinks. What happens then?
It sinks back down towards the surface, creating areas of high pressure. And those high pressure zones, They're typically associated with clear skies and sunny weather.
So rising warm air equals low pressure and rain, while sinking cool air equals high pressure and sunshine. Sounds pretty straightforward so far, but I'm guessing it gets more complicated than that.
You're absolutely right. The Earth's atmosphere is a complex three-dimensional system. All these high and low pressure areas are constantly interacting, pushing and pulling air masses around the planet. Think of it like a giant, constantly churning sea of air with these pressure systems acting like massive whirlpools.
Wow, that's a pretty dynamic image. So those pressure systems are creating winds.
Precisely. Wind is simply air moving from an area of high pressure to an area of low pressure. The greater the difference in pressure, the stronger the wind.
Okay, that makes sense. And what about moisture? How does that factor into all of this?
Moisture, or humidity, is a key player in the weather game. It's what forms those beautiful clouds we see. And those clouds can influence temperature, precipitation, even wind patterns.
So it's like a giant puzzle with all these different pieces: temperature, pressure, wind, moisture, constantly interacting and influencing each other.
You got it. And it's that complex dance that creates the weather we experience every day.
So we've talked about rain, but what about other types of precipitation? What's the difference between, say, rain, snow, sleet, and hail?
It all comes down to temperature, really. Let's start with snow. Snow forms when water vapor in the atmosphere freezes directly into ice crystals.
So it skips the whole liquid phase.
Exactly. And for that to happen, temperatures have to be below freezing, both in the clouds and near the ground.
Okay, so snow is basically frozen water vapor crystallizing directly in the air. What about sleet? That's kind of a weird one.
Sleet is a bit of a hybrid. It starts as snow, but then those snowflakes fall through a layer of warmer air, partially melting.
So they turn to rain.
Briefly, yes, but then they refreeze into ice pellets before they hit the ground.
So it's like a mid-air freeze, okay? And then there's hail.
Hail is definitely the most dramatic form of precipitation. It forms within thunderstorms where there are strong updrafts and downdrafts of wind. So raindrops get carried up and down through layers of freezing air.
So each time they go up, they accumulate another layer of ice.
You got it. And those hailstones keep growing until they're too heavy to stay aloft. Then they come crashing down.
That's wild. It's incredible how those different forms of precipitation all start with the same basic ingredients: water vapor and varying temperatures. But the results are so different. You know, we've talked about wind being air moving from high pressure to low pressure. But wind can be a gentle breeze or a destructive hurricane. What accounts for that difference in intensity?
Well, it's all about the pressure difference between those two areas. A really large pressure difference creates a much stronger rush of air trying to equalize things out.
Okay, so a gentle breeze means a small pressure difference, while a hurricane means a massive difference. But there are also different types of winds, right?
Right. We can think of them in three main categories: permanent winds, seasonal winds, and local winds. Permanent winds blow consistently in a particular direction throughout the year. The trade winds, the westerlies, the easterlies, those are all permanent winds.
Okay, so those are the big global wind patterns we see on weather maps. They drive those major weather systems around the planet.
And then we have seasonal winds, which change their direction with the seasons.
Like monsoons?
Exactly. The monsoon winds are a great example. They bring heavy rainfall to parts of Asia during certain times of the year.
Right. And those monsoons can be both a blessing and a curse. They can bring much needed water for agriculture, but also cause devastating floods.
And then the last category is local winds. These blow only during a particular time of day or year, and usually in a small, specific area. Think of land and sea breezes.
Those are caused by the temperature differences between land masses and bodies of water.
Yep. That's why you get those lovely sea breezes at the beach on a hot day.
It's amazing how these different types of winds, from global patterns to local breezes, all play a role in shaping our experience of weather.
It's all part of the intricate dance of the atmosphere.
Speaking of intricate dances, have you ever wondered how rainbows form? Is it really magic?
Not magic, but pretty close. Rainbows are all about light. They form when sunlight passes through water droplets in the air.
Okay, and what happens to the light?
As the sunlight enters the water droplet, it bends. That's called refraction. Then it reflects off the back of the water droplet. And as it exits the droplet, it bends again.
So it's like the light is taking a detour through the water droplet.
I like that analogy. And it's during that detour that the sunlight gets separated into its different wavelengths, creating the spectrum of colors we see.
So rainbows are a result of the way light interacts with water droplets. What about other optical phenomena, like those halos we sometimes see around the sun or the moon?
Those are formed by the refraction of sunlight or moonlight through ice crystals in the atmosphere. So a similar concept, but with ice instead of water.
It's amazing how these tiny particles in the air can create such stunning visual displays. Have you ever seen the aurora borealis, also known as the northern lights?
I have, and it's truly a spectacle. Those shimmering curtains of green, blue, and sometimes even red light, it's like a celestial dance.
What causes that?
It's all about the interaction between charged particles from the sun and the Earth's magnetic field.
So those particles hit our atmosphere and create those amazing lights.
Yeah, when those charged particles carried by the solar wind collide with atoms and molecules in our upper atmosphere, they energize them. And then those energized atoms release energy in the form of light.
Wow, a cosmic light show, courtesy of the sun. This deep dive is making me see the atmosphere in a whole new way. It's not just the air we breathe, it's a complex, dynamic system that creates everything from the weather we experience to those beautiful displays of light in the sky.
And we're not done yet. In the final part of our deep dive, we'll zoom out even further and explore the bigger picture of climate. We'll look at the long-term patterns and trends that shape our planet and discuss the impact of human activities on the atmosphere.
Welcome back to our deep dive into the Earth's atmosphere. We've explored its composition, its structure, those amazing weather phenomena. Now it's time to shift our focus to the big picture, climate.
And it's important to remember that climate isn't the same thing as weather.
Right, I remember you comparing weather to the atmosphere's mood swings, those day-to-day changes. And climate is more like its personality, the long-term patterns.
Exactly. Think of it as the average weather over a long period of time, at least 30 years.
Okay, so weather is what I check before I leave the house. Climate is the bigger picture, shaping an entire region for decades. What determines a region's climate? What are the big factors?
Latitude is a big one.
Yeah, we talked about that earlier, how different latitudes receive different amounts of solar energy.
Right. The more direct sunlight a region receives, the warmer it tends to be. That's why you have those tropical regions near the equator that are warm year-round. Then, as you move towards the poles, it gets much colder.
Okay, latitude makes sense. What about altitude? How does being higher up affect things?
Think about climbing a mountain. As you go higher, the air gets thinner and the temperature drops. That's because the atmosphere is less dense at higher altitudes. Fewer air molecules to trap heat. So mountainous areas usually have cooler climates than lowland areas at the same latitude.
So you could have snow-capped mountains, even at the equator. That's pretty wild. What about proximity to large bodies of water?
Water is a great temperature moderator. It heats up and cools down much more slowly than land does.
So being near a coast means milder winters and cooler summers?
Generally, yes. Coastal areas tend to have more moderate climates than inland regions.
Okay, that makes sense. You also mentioned ocean currents earlier. How do those giant rivers of water in the ocean affect climate?
Well, they act like massive conveyor belts, transporting warm water from the tropics towards the poles and colder water from the poles towards the tropics.
So they're constantly redistributing heat energy.
Right. And that has a huge impact on the climates of coastal regions, like the Gulf Stream, for example.
That's the one that carries warm water from the Gulf of Mexico up the eastern coast of North America.
And even all the way across to Western Europe, keeping those regions much warmer than they would otherwise be at those latitudes.
That's incredible. It's like a natural heating system. Okay, what about wind? How do prevailing wind patterns influence climate?
Prevailing winds play a crucial role in distributing heat and moisture around the globe.
Okay, so those global wind patterns we talked about earlier, they're not just moving weather systems around, they're also influencing long-term climate.
Exactly. They can pick up moisture over the oceans and bring rain to coastal areas, or they can stay dry as they blow over deserts.
It's amazing how these winds can shape entire ecosystems. But how do we know about past climates? It's not like we had weather stations millions of years ago.
We have something called proxy data. It's like nature's way of keeping records.
Proxy data, what is that exactly?
It's information from natural sources that can tell us about past climates, like tree rings, for example.
Tree rings?
Yeah, trees grow more in warm, wet years, so they produce wider rings, and in cold, dry years, the rings are narrower. So by looking at the patterns in tree rings, we can reconstruct a history of past climates.
So it's like trees are keeping a secret diary of climate change.
What?
What other clues can we find?
Ice cores. They're long cylinders of ice drilled from glaciers and ice sheets.
Okay, and what do those tell us?
Those ice cores trap air bubbles and other particles from the atmosphere. And by analyzing the composition of the air trapped in those bubbles, we can learn about past temperatures.
So they're like time capsules from the past.
Exactly. And it's not just tree rings and ice cores. We can also learn from ocean sediments, coral reefs, fossilized pollen, even historical records like old ship logs.
Wow, it's incredible how scientists can piece together such a detailed picture of the past using all these different sources. But why is understanding past climates so important?
Because it helps us understand how our climate is changing now and what might happen in the future. And that brings us to the topic of climate change.
Right, a term we hear all the time. But what does it actually mean? What's causing it?
Climate change refers to these long-term shifts in global temperatures and weather patterns.
Okay, and those shifts can occur naturally, right?
Yeah.
I remember learning about ice ages and warm periods throughout Earth's history.
Absolutely. Natural factors like volcanic eruptions and variations in solar radiation can cause climate to change. But what we're seeing now, this current warming trend, is different. It's happening at a rate that's unprecedented, and it's largely driven by human activities.
And the main culprit is the burning of fossil fuels,
Right. Burning fossil fuels releases greenhouse gases into the atmosphere.
like carbon dioxide.
Exactly. Carbon dioxide, methane, nitrous oxide. These gases act like a blanket around the Earth, trapping heat from the sun.
So the more greenhouse gases we pump into the atmosphere, the thicker that blanket gets.
Exactly. And that's what's causing the planet to warm up. It's enhancing the natural greenhouse effect.
And we're already seeing the consequences, right? Rising sea levels, more extreme weather events. It's a global issue with no easy solutions.
You're right, it's a complex challenge. But it's not hopeless. There are things we can do. We need to transition to cleaner sources of energy, reduce our reliance on fossil fuels, invest in energy efficiency, protect our forests.
It sounds like a massive undertaking.
It is. But it's also an opportunity to innovate and collaborate to create a more sustainable future.
This deep dive has been an eye-opening journey through the layers of our atmosphere. We've learned about its composition, its structure, how it creates our weather, the long-term patterns of our climate, and the impact we humans are having. It's clear that the atmosphere is far more than just the air we breathe.
It's a complex, dynamic system that makes life on Earth possible.
And it's a system we need to protect. Knowing what we know now, it's up to each of us to do our part to make those changes to ensure a healthy atmosphere for generations to come. Thanks for joining us on this deep dive